This is section 15.7 on maximum and minimum problems. Section 15.7 and 15.8 are both different ways of finding maximums and minimums. You should care about maximums and minimums because the main reason math is used in the world is to optimize things. To optimize things, you say you want to optimize the price. You want to minimize the price of making something. Then you make a function that represents the price with all of its inputs, and you minimize that function. You find an extreme value. Now, the issue is that in Calculus 1 and Calculus 2, when you did optimization problems, you could only have one input because your functions were functions of one variable. But in reality, the price of creating an object depends on at least 4 different things, maybe even more. So you need calculus of multiple variables, namely this class, to figure out how to do that. So let's do it. So the objectives will be to find some critical points. Critical points were something from Calculus 1, but we still get to use them here. And then we'll use something called the second derivative test, or the second partials test, to figure out what kind of critical point you're looking at. So let's just think back to how this worked in Calculus 1. In Calculus 1, your functions looked like maybe like this. You had one input, and your output was one number. Critical points were the points where the first derivative equaled 0 or did not exist. So like this function as drawn has 3 critical points. Some of these points were maximum values. This one is a relative max. This one was a relative min. And this one was neither. So what we would do if we were trying to find all the maximum and minimum values in Calculus 1 is we would take the derivative, set it equal to 0, or find where it didn't exist to get the critical points, and then those critical points were the candidates for the extreme values. Then we needed to use some kind of test to figure out which ones were maximums, which ones were minimums, and which ones we needed more information about or were possibly neither. The outline is just going to be exactly the same in this class. I kind of want to remind you what the second derivative test was, but I think maybe we'll do that later. Okay, so in Calculus 2, we also want to decide what it means to have a relative minimum. And what we'll do, just like in Calculus 1, this counted as a relative minimum because it was the lowest output value for all nearby input values. Well, here, to have the lowest output compared to nearby inputs, now the inputs are x's and y's. So we'll say, well, as long as you have a disk where, a disk of inputs, a disk in the plane of x's and y's, where this point is the lowest output for all the points in the disk, it counts as a relative minimum. So in an open disk containing x0, y0 is our technical way of saying near x0, y0. And same deal here. Is there something else I wanted to say here? No, that's about right. Okay, so how does that happen? How can you have a relative maximum or a relative minimum? Well, the main ways that can happen are if you're at the top of a hill, or if you're at the bottom of a hill, or if there's a cusp or a corner or something. So that's how this will work. If you're at the top of a hill or the bottom of a hill, then the partial derivatives, both x and y, will equal 0. If you're at a cusp or a corner or something, then you'll have a partial derivative that does not exist. So if either one of these is the case, then we will call it a critical point. So just like in Calc 1, take the derivative, set it equal to 0, or see if it doesn't exist. Here in Calc 3, it's take each partial derivative and set them all equal to 0 at the same time, or find one of them that does not exist. And those will be the critical points. Those critical points, those aren't the maximums and minimums, because there might be some weird ones that are not maximums or minimums, but those critical points are the candidates for the extreme values. Okay, so first let's practice finding critical points. This one, it looks like its partial derivatives always exist. These are polynomials, so nothing bad is going to happen. So let's find the first derivative. Let's find the first partial derivatives, and we set them both equal to 0. The key thing here is that we're setting them both equal to 0 at the same time. So it's not like this is two separate answers. It's like both of these have to be true at the same time. So it's this first one and the second one, not or. It's not like two solutions to a quadratic equation. It's like both of these have to be true at the same time. Okay, how could 2 times x minus 2 equal 0? Well, that's either 2 equals 0 or x equals 2. And then how could half y minus 4 equal 0? Well, that's either half is 0 or y is 4. Okay, I mean, half doesn't equal 0 and 2 doesn't equal 0. So there's only one critical point. It's the point where x equals 2 and y equals 4. Sometimes you'll get multiple critical points. Here we got one. Notice that this critical point, it might be a maximum. It might be like the high point of this surface, or it might be the low point of this surface, or it might be neither. But this critical point is it's our candidate for a maximum or a minimum. Okay, let's look at this one. This one looks like it has some potential problems. There's a square root. When I take the derivatives, I'm going to get stuff in the denominator, so I have to pay attention to whether the derivatives exist. So first I'll find the x partial derivative. This is a huge big square root, so its derivative will be 1/2 times the whole big square root, like the thing inside there, to the minus 1/2. This already has a name. It's called g. And then times the derivative of the inside function, which here is going to be minus 2x minus 1. The 2's cancel, so I get minus x minus 1 is what I was going to write. How about 1 minus x over the output? The y partial derivative, same thing is going to happen, except this time I'll have minus 2y plus 3, all divided by 2 times this g. Oh dear, this square root is not actually all of g. G has a minus 2 in it. So g is this big square root, minus 2. So if I want a short way to write the gross square root, I need to write that it's g plus 2. So I'll have, for the y partial derivative, minus y minus 3 over g plus 2. Okay, so what's the problem? It would be easy to set gx and gy equal to 0, but we need to remember to be worried a little bit about whether these actually exist. So like g plus 2 is sitting here in the denominator. I'm worried that g plus 2 might ever be 0. So let's investigate that first. That happens if square root 16 minus x minus 1 squared minus y plus 3 squared all equals 0, which seems like it could happen. Like if I square both sides and move the squares over to the other side, I get 16 is x minus 1 squared plus y plus 3 squared. So there's a whole circle here where the derivatives do not exist. So this seems a little bit crazy because all these points would be critical points. So we need to look back at the question and make sure that we didn't miss something. Find all critical points of the function where x minus 1 squared plus y plus 3 squared is less than 16. Okay, so the question tells us that we're not supposed to worry about when this quantity equals 16. It's always going to be less than 16. So this never happens because of how the question is worded. So we're safe. So the derivatives always exist, which means we can set the derivatives equal to 0 to get the critical points. So the x partial derivative equals 0. You can make this fraction 0 by letting x equal 1. And the y partial derivative equals 0. Well, you do that by letting y equal minus 3. So the critical point, this surface only has 1. is at 1 minus 3. So yeah, it's just not that bad. You just take both partial derivatives, set them both equal to 0 at the same time, and you'll get some points. You need to worry to make sure, like, if there's a single point where the derivative does not exist, that's also a critical point. Okay, here's one more. These derivatives are always going to exist, so we'll just find the derivatives and set them equal to 0. These both happen at, this one happens at x equals 0, and this one happens at y equals 0. So the critical point is 0, 0. So critical points are supposed to be not scary. You take a bunch of partial derivatives, set them equal to 0. Okay, the issue is that once you know how to find the critical points, they're not all maximums and minimums. So compute all the second derivatives at all the critical points you found for all the different functions. Okay, all second derivatives. So there's 3 different kinds of second derivatives. There's the second derivative where you do xx, there's the second derivative where you do yy, and then there's the mixed partial derivative where you do one and then the other. So they all had different names. Let's copy down what fx and fy were so we can work with them. Oops, not the first page. Fx was 2x minus 2, and fy was half y minus 4. Okay, to get second partial derivatives, well, you can find fxx. This is the x partial derivative of the x partial derivative of f. So we take one more partial derivative of this one, and we get 2. The y partial derivative of the y partial derivative of f here is a half. And if you find fxy, that would be the y partial derivative of 2x minus 2. That's 0. And as we found earlier, we don't have to find fyx. Fyx and fxy will equal each other anywhere that all the partial derivatives are defined. So this is the mixed partial derivative. So this equal sign between here is me trying to tell you, you don't have to find both of these every time. Okay, why are we doing this? Like, what's the point of this? The point of this is the second derivative test is going to be the way that we tell whether a critical point is a maximum or a minimum, or maybe we don't know. So we want to investigate all these second derivatives to see what happens. So here I had gx was 1 minus x on top, and gy was minus y minus 3. It's kind of a mess. I guess let's find gxx. I don't see any way around this. I'll have to do the quotient rule. So I have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now the derivative of the denominator here is gx. All divided by the denominator squared. Now, what are we doing? We want a number here, and so I'm going to have to like plug in the x and the y into this. The fact is that we already know gx equals 0 at the critical point, so this part is gone. So I can cancel a g plus 2 with another g plus 2, so I get minus 1 over g plus 2. Okay, I guess we're going to have to go back to look at what this actually comes out to. G plus 2 was this square root. At the critical point, which was 1 minus 3, we were getting rid of all these. So g plus 2 is going to equal 4. So this is minus a fourth. That's gxx. gyy, same deal. Do the quotient rule. Minus numerator times derivative of the denominator, all divided by the denominator squared. gy is 0 at a critical point. G plus 2's cancel, and I get minus 1 over g plus 2 again. That's cool. A little trickier will be to find gxy or gyx. I'll just find gxy, which is the y partial derivative of gx. So I'll have the denominator times the derivative of the numerator, but the numerator has no y's, so the derivative of the numerator is 0, minus the numerator times the derivative of the denominator, that's gy, all divided by the denominator squared. We are at a critical point in this question though, so gy is 0, and here's another 0, so this whole thing came out to 0. The mixed partial derivatives are not always 0, but when the mixed partial derivative is 0, it'll make it easier for us to like imagine what's going on with the surface. Okay, this is a lot of busy work, so I don't think I'm going to do... I guess the other one is like really easy, right? So here hx was minus 2x, so the second derivative xx is going to be minus 2. The second derivative with respect to y is 1/2. This one also has a mixed partial of 0. This is pretty uncommon. They usually aren't 0. It's just for the purpose of introducing the second derivative test. This is easier to see. Okay, so let's get some pictures of these three functions. One of them I have both partial derivatives are positive. One of them I have both partial derivatives are negative, both second partials. And the other one I have one of each. I guess I just want to, I mean, I'll get the graphs up there in a second, but I want to convince you that what's about to happen like makes sense before we see the nice graphs of the surfaces. So I'll use my high-tech devices here, which are these paper clips that have been curved with some post-it note taped to them. So when a second partial derivative is positive, that represents in the x direction, so like kind of coming out of the camera, the curvature of the graph is concave up. So a second partial derivative in the x direction being positive looks like this, in this direction. The rest of the surface could do who knows what in all the other directions, but in the x direction, it's concave up. Where if, like for gxx is negative, that means that in the x direction, the curve is concave down. Okay. What does it look like if fxx and fyy, which is in the other direction, are both positive? So you have like it's curved up in the x direction and it's also curved up in the y direction. Then you have like the bottom of a bowl. And in that situation, it's a relative minimum. This is the low point of the surface. So when they're both concave up, that's the minimum of the surface because it's just like concave up and concave up. So this one is going to be a minimum. If you have both of them concave down, now it's like concave down this way and it's concave down this way. Now you can kind of see that you'll end up with a bowl that's upside down, and this is a maximum point of the surface. So this one will be a maximum. What else could happen? Well, what else could happen is that they could disagree. So you could have like it's concave down in one direction and concave up in the other direction. And when that happens, your surface doesn't have a maximum or a minimum there. Instead, this is what's called a saddle point. It's called a saddle point because like this is what a saddle looks like you could ride in the saddle here. So if it's concave up in one direction and concave down in the other, those disagree, you get a saddle point. Now, that doesn't always exactly happen because the mixed partial derivatives come into play here, but this one is neither a max nor a min, and that's the idea for the second derivative test that we're going to bring up here in a minute. the mixed partial derivatives have to do with like if the curvature is crazy, like off, like maybe off in a diagonal direction. But yeah, the main idea is like the second derivative test says if everything is concave up, that's a minimum. If everything is concave down, that's a maximum. And if there's some disagreement somehow, then it's probably neither because it's like a saddle point. So let me get like a GeoGebra picture of the saddle point. This is geogebra.org/3D. Where's my... So the saddle point was the function h. It was y squared over 4 minus x squared. So in one direction, it looks concave up. In another direction, it looks concave down. When you have that, like, I don't know, disagreement, you get a saddle. I'm going to move it up a little bit so we can get the saddle off of the xy plane so you can maybe see it a little better while it's spinning. This is a saddle point. And that's what I was trying to like illustrate with. Just make it concave up in one direction, concave down in another, and you get a saddle. I'm getting dizzy here. I'll get the first one too. So the first one was it had an x squared and a y squared and they were both positive. In this case, both of the second derivatives are positive, and when both second derivatives are positive, it's concave up in both directions. You get a bowl, and that point is a minimum. So if we combine all this together, we can make a second derivative test for surfaces, a second derivative test for functions of two variables. If I can find the page. Where's like the fact? Sorry, I want a page of the notes that has like a box and says how the second derivative test works. Oh, it was the page I was on. Sorry. Okay, so the second partials test says, let's use the second derivatives, the second partial derivatives, to see if something is a positive, is a minimum, a maximum, or a saddle. So for now, to try to make sense out of this discriminant, for now, ignore the fxy term and just imagine what happens with fxx and fyy. If fxx and fyy are both positive, then you got a minimum. And if they're both positive, then multiplying them together would cause a positive number. So this is a d is positive situation. If they're both negative, multiplying them together also gives you a positive number. So the d is greater than 0 situations look like this or like this. So we should expect the d is greater than 0 situations to give us maxes and mins. Where if fxx is positive but fyy is negative, they'll disagree, and multiplying them will give you a negative number. So a negative d represents a saddle point. I'm not getting into the details of why fxy matters, but please like use the fxx fyy as like the reason why this makes sense to find d, and we don't have time to go into all the details of why this works. So in total, to decide whether your critical point is a maximum or minimum, you find d. So you first, where's the critical point? So you say, I want to know if it's a max or min. First you find a critical point, then you find d. If you have a positive d and fxx is positive, that puts you in this situation. You're at the bottom of a bowl. So this is a relative minimum. If you have a positive d, but things are concave down, that's a relative maximum. If d is negative, it's a saddle point. Now, there's one more thing that can happen, which is that you can find all this stuff and get that d is 0. If d is 0, then this test is not good enough. and you need some other information to finish the problem. I think for this class, the questions will all have a d that's not 0, but you should maybe remember that the second derivative test sometimes came out inconclusive in Calc 1 also, and it wasn't a disaster. It was fine. We just found some other way to deal with it. But that's the outline. Find the critical points. Use this second derivative test to figure out whether those critical points are mins, maxes, or saddle points. Let's do it. So here's a surface. It's given by a function where the input is 2 variables and the output is 1 number. So the input is a point in the plane, and this is how high the surface is. If someone asks you to find relative extrema and saddle points, you go looking for critical points first. When you're writing stuff, you should write these words. You should tell me what your plan is. So we're going to need fx, which is minus 3x squared plus 4y. We need that to equal 0, and we need fy to equal 0. At the same time. Because you have an and here, that means that this is basically a system of 2 equations in x and y, and you're trying to find the places where these 2 equations are both true. The easiest way to solve a system of equations is to use substitution, which is solve for something in some equation and substitute it into the other one. This equation over here on the right looks a lot easier to me, so I'll deal with this one. So I'll divide both sides by 4, and I get that y equals x. And I'll substitute that into here. This is a quadratic. I'll solve it by factoring. So I get that either x is 0 or minus 3x plus 4 is 0. So here x is 4/3 or x is 0. This is 2 critical points. You combine whatever you found from the result with whatever you used to do a substitution. So here it told me y equals x, which means I can turn both of these into points that have the same y as x. If this said y equals 2x plus 3, I would use that to find what y was. So these are my critical points. I've got 0, 0, and 4/3, 4/3. These 2 critical points, maybe one of them is a max and one of them is a min, or maybe they're both saddles or something. There's some crazy service going on here. So let's figure out which is which. We'll do the second derivative test on both. Some people call it the second partials test. To use the second partials test, we need fxx, which here is the x partial derivative of fx. So fxx is minus 6x. We need fyy. That's the y partial derivative of fy, which is minus 4. And we need fxy, which should be the same whether we take the y partial derivative of fx or the x partial derivative of fy. And either way we get 4. The second partials test, you do it separately for each point, because each point might have a different curvature or a different arrangement of what's going on the surface there. So for 0, 0, we're going to use the second partials test, which is find d. At this point 0, 0, fxx is 0. So I get 0 times minus 4 minus 4 squared, and I get minus 16. So because d is negative, I'm done. It's a saddle point. If d is positive, then you check which situation you're in, whether you're in the bowl that's up or the bowl that's down. Let's look at the other one. At 4/3, 4/3, find d again. Here, fxx isn't 0 anymore. It's -6 times 4/3, so that's like -8. fyy and fxy are fixed at -4 and 4, so those we don't have to calculate again. But this time I get 32 minus 16, so I got plus 16. That's greater than 0, which means it's either a maximum or it's either a minimum or a maximum. To find out which one it is, you look at fxx and fyy. Here, fxx and fyy are less than 0. They're both negative. fxx being negative and fyy being negative mean that the picture looks like this, so it's a maximum. It's a relative maximum. So whatever's going on with this surface, it's got a saddle at 0, 0 and a relative maximum at 4/3, 4/3. Because we live in a world where we can just like get a nice picture of the surface, let's use that fact. So I'm back on geogebra.org/3D. The surface was z equals -x cubed plus 4xy, oh dear, minus 2y squared plus 1. So the surface is, I don't really want to spin that fast. The surface is pretty complicated, but it does have a saddle here at x equals 0, y equals 0. And it has a maximum point here, somewhere in the positive x's and positive y's, and that must be at 4/3, 4/3. So surface is kind of crazy, but with just a little bit of first partial derivatives, you can find the two critical points. And then using the second partial derivatives, you can figure out what kind of critical points those are. Saddle points, or we had a maximum for the other one. It's kind of awesome. Neat. What's next? Wait, was there more on this page? No. Okay, next up is, that's nice. Thank you for finding like maximums and minimums of functions. But here we will say, well, in the real world, we want to maximize or minimize real like physical quantities. So here it says, find the maximum volume. If someone asks you to maximize a thing, then that is called the objective function. So this is the plan. Find the objective function. The objective function is the thing you are trying to optimize. Sometimes you're trying to optimize the amount of time something takes. Sometimes you're trying to optimize the amount of money something takes. Maybe sometimes you're trying to optimize the amount of space. Here we're trying to optimize the amount of volume. So the objective function here will be a volume function. After you find the objective function, then you use this process with the critical points and the second derivative test on this function. The danger of these problems is that often students skip this first step of picking out what is the objective. They just go like, I don't know, here's some, there's an equation there, x plus 2y plus 5z equals 10, and just like try to use it. But that's not what's going on here. When the question asks find the maximum volume, you have to start by finding a formula for the volume, and then work with that function. Okay, so what are we doing? Find the maximum volume of a rectangular box. So it's going to be a box, so it's going to be length times width times height. One vertex is at 0, 0, 0, and the other vertex is on the plane x plus 2y plus 5z equals 10. Okay, so there's some plane out there. And you're fixed at the point 0, 0, 0. And then the question is, well, if I pick a point out here, x, y, z, what volume do I end up with? Of this box. So here's 0, 0, 0. Drawing this little tiny schematic diagram lets me get away from the fact that this plane has like its own equation, and it lets me get away from the distractions of the question. The little schematic diagram and my plan tell me like, oh, all I'm trying to do is find the length, width, and height for now. The length of this box is x, and the width is y, and the height is z. So the volume, like the objective function, is xyz. That's my volume function. Small problem. This method only works for functions of two variables. So we need this to be a function of two variables before we can continue. That means we will need to look at some other information in the question and get one of these variables in terms of the other two. And that's where x plus 2y plus 5z equals 10 comes into play. I could solve for z and write z in terms of x and y. I could also solve for x and make everything in terms of y and z. Solving for x would make it much easier because there wouldn't be any fractions. I'm kind of tempted to do that. But this is the first example. I guess I'll solve for z to get everything in terms of x and y, but you should know that this method of the mixed partial derivatives with the critical points, it works no matter what the variables are called. Nah, I shouldn't sissy out on you. I should make the problem easier when possible. So the easiest thing to solve for is x in terms of these other things. So I'll notice that x is 10 minus 2y minus 5z. And we'll end up with the volume as a function of y and z. So it was xyz, but here's x. 10 minus 2y minus 5z. yz. So here's my objective function. I think it's worth it because I'm going to be doing stuff with this function. It's worth it for me to multiply this out. As usual, I recommend against simplifying stuff unless you have a reason to. The main reason would be that you're going to use it later. Here, I'm going to do a bunch with this later. So yeah, I'm going to multiply it out and simplify it as much as possible. So this is my objective function. It's a function of two variables. The goal is to find the maximum volume. So I'm trying to find the maximum value of this function. Well, to find the maximum of a function, you go looking for critical points. Do you see how this question is the same as the previous question now? But this stuff up here, the process of finding the objective function, is new from the previous example. The previous example just gave you a function and asked you to find some critical points. This one is like, here's a situation, find the maximum. And the first step is to get the objective function in a situation where we can do what we did in the last problem. So here my two variables are y and z. So critical points are where vy is 0 and also vz is 0. Let's find vy. Vy is 10z minus 4yz minus 5z squared. And vz is 10y minus 2y squared minus 10yz. And these are supposed to equal 0 at the same time. I guess these all have a factor of z in common, and these all have a factor of y in common. So I'll just do that. I'm thinking of this as a system of two equations that I'm trying to solve simultaneously. Factor out a y over here. Z equals 0 is going to be one of the possibilities. Y equals 0 is going to be one of the possibilities. But I know z equals 0 is not going to give me the maximum volume because the volume is x times y times z. And I also know that y equals 0 is not going to give me the maximum volume. So I'm going to throw them out now and end up with 10 minus 4y minus 5z equals 0 and 10 minus 2y minus 10z equals 0. Okay. The easiest way to solve a system of two variables is to solve for one and substitute it into the other. It looks like the easiest one to solve will be the right-hand one, solving for y, because I can divide both sides by 2. And then just solve for y by adding it over to the right side. So y is 5 minus 5z. And I can put that in this equation to get 10 minus 4, 5 minus 5z, minus 5z equals 0. So we're just doing some system solving. After you do substitution, you get one fewer equation and one fewer variable. So this is just one equation in terms of z now. So we can solve for z. It's going to be 10 minus 20 plus 20z minus 5z all equals 0. I end up with 15z is 10, so z is 2/3. This is not a critical point. For this function, the inputs are y and z, so I need to know what y is. But luckily, from doing substitution, I'm ready to go. Y is 5 minus 5z. This is 15/3 minus 10/3, so this is 5/3. So the critical point is y equals 5/3, z equals 2/3. Now I feel pretty confident that this is the maximum volume because the minimum volumes were these ones where y was 0 or z was 0, but we should use the second partials test to make sure. So to see, we're hoping this is a maximum, so we'll do second partials. I need to find vyy. Vyy is minus 4z. I need vyz. Vyz and vzy should be the same, but let's make sure. Vyz looks like minus 4y minus 10z when I calculate it using vy. Over here, when I take the y partial derivative, I get 10 minus 4y minus 10z. Should this one have a 10 also? Oh, it does. Okay. So vyz is actually 10 minus 4y minus 10z. And then vzz is the z partial derivative up here, which is minus 10y. Since we only have one point to check, I can just plug all this in. So here vyy is minus 8/3. Vyz is 10 minus 20/3 minus 20/3. So this is 30/3 minus 40/3, which is minus 10/3. And vzz is minus 50/3. To make sure we have a maximum, we calculate this discriminant. D is the partials where we do the same variable multiple times, minus the mixed partial squared. Let's see what we get. We get 400/9 minus 100/9, which is 300/9. And I don't really care what 300/9 is. All I care about is that it's positive. So D is positive. That means that we're in a maximum or minimum situation, like this or like this. But both of the mixed partials were negative, so we're in this situation. So that means that between this and this is a maximum. So that means we've found the situation, like this is the right one. This is the point that gives the maximum volume. Let's make sure that we actually answer the question. The question asks for the volume. So when the question asks, what's the maximum volume? Answering y equals 2/3 is like not the answer to the question. The answer is the volume. Luckily, when you've made an objective function, you're always prepared to get the answer, that kind of answer. You just plug your critical point into the objective function. So it's 10yz minus 2y squared z 2y squared z minus 5yz squared. When I have y and z here, y is 5/3 and z is 2/3. So this is going to be 10 times 5 times 2 ninths. Why is it 10yz? The units don't match. Is 10yz correct? Hang on. Yeah, I guess so. Yeah, no, okay. And then 2y squared z. Okay, so that's going to be 2 times 25 times 2 on top. And the denominator has 3 3's, so 27. And then minus 5 times y times z squared. And the denominator is 27 again. So what do we have in total? This is 100 ninths. That's 327ths. Minus 127ths. Minus, is this 100 also? So this is all over 27. So the answer is that it's 127ths is the maximum volume. Does that seem about right? It's about like 1 by 2 by something. 1 by 2 by something. It's going to be like in the range of like 1 to 10 is going to be our volume. And this answer is about 3 or 4. So this seems about right. So this is our maximum possible volume in this situation. The outline was, first find the objective function. Don't dive into the calculus right away. You're going to do like a geometry or a physics or an economics question first, where you figure out what is the thing you're trying to optimize. Then you go into calculus, where you find critical points and use the second partials test on whatever you just found. Nice. Okay, we're going to do one more. It's a real world example. This is a real actual restriction on boxes that can be shipped by USPS. I guess I haven't checked this year, but at least last year, well, it's been the rule for a long time. So the rule is actually that the girth plus length of a standard post package cannot exceed 108 inches. So, and then the question will be, okay, based on this weird restriction, what are the dimensions that give you the maximum volume? So again, we're trying to maximize the volume. And I've got a box here. I'll say that it has length, width, and height. The objective is the volume. The restriction is that the length plus the girth needs to be 108 or less. So we'll say the length plus the girth is 108, but the girth is how far it is around the package, which is 2 widths plus 2 heights. So I've got my objective function. It's a function of 3 variables. I know that just like last time, I'll need to get my objective function down to 2 variables so I can use calculus on it. To do that, I need some restriction. In the previous problem, that one of the points was like on a plane and we had an equation for it. Here, the restriction is your box can't be massively huge. If it's really long, it can't be very far around. And if it's really far around, it can't be very long. It's this restriction. So we'll use this restriction to get our objective function down to 2 variables. Again, you pick whatever variable you want to solve for, and here it's easiest to solve for L, so I'll get my objective function in terms of width and height. It's going to be L times W times H, but L is 108 minus 2W minus 2H. I just really want to emphasize the strategy here, that the strategy did not start with calculus. It started with writing down the objective function. And then noticing that we need the objective function to be a function of two variables. That's this one. Once your objective function is a function of two variables, now you can mash it into the calculus machine and see what happens. The calculus machine looks like this. You find critical points. A critical point is where both partial derivatives equal 0 at the same time. So here's the w. Oh, I didn't multiply it out. Since I'm going to be doing more math with this objective function, I clearly should multiply it out. I don't want to be doing the product rule over and over. So this is 108wh minus 2w squared h minus 2wh squared. So the w partial derivative of our objective function is 108h minus 4wh minus 2h squared. And I need both partials to be 0. So this equals 0, and the h partial derivative needs to equal 0. These are supposed to happen at the same time. So this is a system that I'm solving, and I'll use the same trick I've been using repeatedly, which is whenever I have a system I'm solving, I try to get a handle on the equations first, maybe by factoring them or something. This time, I again have common factors, where there's an h in common over here. And there's a w in common over here. This is going to give me two solutions. It's going to tell me, well, okay, either h is 0 or 108 minus 4w minus 2h equals 0. But a package with height 0 is not going to be the winner here. So I'll throw that one out. And similarly, I don't need to worry about the width of my package being 0. That's not going to be the right shipping plan. These equations look like they're the same equation, but this one has 4w and 2h. This one has 2w and 4h. I'm trying to solve these two equations at the same time, so I'll use substitution. Pick any equation and solve for anything in it. I don't know, this time I'll solve for h in the first equation. So divide through by 2. And solve for h. h is 54 minus 2w. And I can substitute it into my other equation. What I'll end up with is one less equation, one fewer equation, and one fewer variable. This I can just solve for w. So I'll have 108 minus 2w minus, this is 216 plus 8w, all equals 0. So 6w is 108. So w is 18 maybe? 18 times 6 is 60, 48. Yeah, so w is 18. That's not the critical point. The critical point would be a point wh. So I'll go find h now. Luckily, this always happens when you do substitution. There's always a formula out there that will tell you what h is. Here, h is 54 minus 2w. So h is also 18. So the critical point is at 18, 18 for w and h. Now, I'm pretty sure this is going to be the maximum again, but while we're here, we'll do the second partials test. VWW, so we'll find all the second partial derivatives. VWW looks like minus 4h. VWH is 108 minus 4w minus 4h. To check our work, we'll also find VHW, which is the w partial derivative of VH. So we get 108 minus 4w minus 4h, and it's the same, so we feel good about it. And then VHH is minus 4w. what's 4 times 18? It's 40, 32, so it's 72. So this is minus 72. This one is also minus 72. What a mess. This is 108 minus 72 minus another 72. I think it's minus 36. They're all negative, so... wait, if they're all negative, does that guarantee anything? No, it doesn't. So it actually matters what this is. Let's make sure we have this right. 108 minus 72 is 36, and 36 minus 72 is negative 36. Yeah, okay. So we're now trying to figure out if this is the best possible box, the worst possible box, or some kind of weird saddle point of the boxes where it's not the best or the worst. To find that out, you find the discriminant. VWW, VHH minus the mixed partial squared. So it's going to be negative 72 times negative 72 minus negative 36 squared. If this D comes out positive, then it's a max or a min. If the D comes out negative, it's a saddle point. This looks like it comes out to 3888. This is greater than 0, so it's a max or a min. Then, since both VWW and VHH are negative, my picture in my mind is like a negative second derivative is something that's concave down. So that means both directions are concave down, which means this is a maximum value. So we did it. We found the best possible box to ship through USPS. It has a width of 18 inches and a height of 18 inches. This is the largest volume box you can ship through USPS. I guess that's not really done. The question asks, what are the dimensions of the box? So we should find L. L is 108 minus 2W minus 2H. So this is 108 minus 36 minus 36, which is 36. So the largest possible box to ship through the US Postal Service is 36 by 18 by 18. I don't know if they designed this system on purpose because they like this size box. I have no idea. But this is the true answer of how the US Postal Service works. This is the best possible box. Okay, so that's 15.7, maximum and minimum problems. You got the idea of a critical point, which was to set all the first partial derivatives to 0. And then you got how to figure out what kind of critical point that was using the second partials test. And then for the last two questions, you learned how to build an objective function based on the question. And then that kind of objective function is the kind of thing that you'll actually use critical points and the second partials test on. So practice this a bit and you'll be an expert. In 15.8, we'll figure out how to do these maximum and minimum problems without finding critical points. The cost will be, we'll have to do more algebra, but we'll do less calculus. 15.8 is super awesome. Well, you'll see.